Now we have a different situation. I'm showing you a plot of velocity, and notice that your velocity is not a horizontal line. Your velocity itself is changing. Now, I'm not going to talk about how we get position from this. There's a separate video that talks about position from velocity. But right now, I just want to talk a little bit about acceleration. So acceleration, in this case, note that you have velocity in the x direction. So what we can determine from this is your acceleration in the x direction. And we can talk about this as a change in velocity divided by a change in time, or a time interval. And so what we see is that this is a straight line, again, not horizontal, and so we have a constant slope all through here, which means we have a constant acceleration. Now we have a different acceleration, but it's still constant here and here. So we have actually kind of two time intervals to worry about, our first one here, and then our second one here. So our first acceleration that I can call A1, just to represent that first time period, I could calculate that as our velocity, our change in velocity our final was 10 meters per second, our initial was 0 meters per second, and the time interval that happened over was 4 seconds. And so that first acceleration is equal to 10 meters per second divided by 4 seconds, and that's going to be 2.5 meters per second squared. And note here to get I've used units every single step of the way, and so I have a meter divided by a second, I've divided by another second, so you multiply them together and you get meters per second squared. So this was constant acceleration, and note that this is positive. I don't always write the positive sign, but it is implied. So this is what a uniform acceleration plot is going to look like, and again, we can approach this in a piecewise manner. So now I'm going to look at my second segment here, and I'm going to look at this from 4 to 12 seconds. Note that it keeps going, but there's a nice kind of end point there. So if this is going to be our A2, again, we can say that this is going to be my change in velocity. So that's my final velocity, which is negative 10 meters per second, subtracted from my initial velocity, which is positive 10 meters per second. And then I'm looking at that time change, which in this case is 8 seconds. Not 12, but I'm looking at what this delta t is, and this is equal to 8 seconds, since that's 12 minus 4. So 8 seconds. So A2, my second acceleration, is negative 20, don't drop that negative sign, divided by 8 seconds, which is, again, equal to 2.5, but negative 2.5 meters per second squared. So what that means is that we have the same magnitude of acceleration in our first and our second region, and you can see that, right? The magnitude of the slopes look the same, but here it's positive and here it's negative. So what this actually looks like is that initially, in this first region, our object is starting from rest and is speeding up. It's moving to the right, the positive direction, and it's speeding up. At this point, it starts slowing down. Now be careful, it doesn't mean that it stops moving, but it starts slowing down. It's still moving to the right. So this whole region here, it is in fact moving to the right. Your v is in the right direction. Now, at t equals 8 seconds, here, it's actually stopped. Your v is equal to 0. And then in this section here, v is now moving to the left. So it is speeding up, speeding up, speeding up, moving to the right, and slowing down. Your acceleration is negative, so it's moving to the right but slowing down until it stops, and now it's moving to the left. It's turned around. So that's how you would analyze this situation. And again, we've assumed that we have a constant velocity, and it certainly looks like it because you have the same slope in all of this. So your acceleration is related to a change in velocity, and it's easiest to figure out acceleration either directly from a plot of acceleration, which we could create, or a plot of velocity. It's fairly hard to get acceleration from a plot of position, so normally we would talk about it if you know something about your velocity or about the physics overall of the situation. So briefly now I want to compare two different lines which are on a position versus time plot. So for A, note that you have a straight line in position. This means that V is constant. Since V is constant, we know that A of x equals 0. Now B, on the other hand, we have a curved line. And again, in a different video, we'll talk about instantaneous velocity. But in this case, we have a changing velocity. And so we have an acceleration that is in fact not equal to 0. Now it's a little challenging to just look at this shape and know if it's the correct shape or not for a constant acceleration, and I would guess that it probably is, but it's really hard to just know that and know that it has the right shape. But normally in our situations, we will have constant acceleration. But the most important thing to know is you have a changing velocity here, you have a constant velocity in situation A, so you have 0 acceleration in situation B, in A, sorry. You have a non-zero acceleration in situation B, which we may or may not assume is constant. We would need more data to know for sure, one way or another. So far we've talked about plots, either velocity or position versus time plots, but remember that motion diagrams are also really helpful. So this motion diagram shows a situation, for instance, of a skier who's on a flat surface, traveling forwards at a constant speed, and then reaches a hill where the skier starts going downwards and accelerating. Now, this would be something a little more challenging to show on a position or a velocity versus time plot, since this is actually two-dimensional motion. But in this case, you can see that we can again break it up piecewise, that up to this point, we're only working really in one direction, and after that point, we're working in a different direction. So we have one-dimensional motion here and one-dimensional motion here. Now this initial motion was a constant velocity, and that means that our acceleration vector was 0. And we show that with this 0 vector symbol up here. So the green arrows are our velocity vectors, but that 0 vector represents our acceleration. Now after that breaking point where our skier starts going downhill, we now have an acceleration vector which you can create by doing vector subtraction of your final and your initial vectors. Now it's in the same direction as motion, which isn't perfectly horizontal or perfectly vertical, but it's still all one-dimensional, it's still in a line. Now one thing to note, if you don't know how to do this, other videos have in fact covered how to create acceleration vectors and how to do vector subtraction. So if this looks strange to you, how you actually would do this vector subtraction to get your change in velocity and then create acceleration, please go back and watch those other videos. The important thing to note here is that even though this motion is somewhat complicated, and you might think that you need two-dimensional motion to describe it, by making it into piecewise, two different sections of motion, you can describe each of them as one-dimensional motion. That first part being uniform motion with 0 acceleration, and the second part with constant acceleration. So when you have more complicated motion situations, ask yourself if you can break it into segments of motion that each can be simplified, for instance, into one dimension, or using uniform acceleration, or just uniform velocity. So the last thing that I would like to cover with acceleration is really reiterating how the direction of acceleration relates to the direction of velocity. And this is something that a lot of people get tripped up on, so that's why I've reiterated it over and over again. Now, the first situation, A here, is the simple one, where you have a velocity to the right, so we would call it positive, and an acceleration to the right, we would call it positive. Note that your velocity vectors are getting longer and longer. And since this is a motion diagram, we know that each of these points represents a later motion in time. So if our motion has started to the left and gone to the right, and we have an increasing velocity with a constant acceleration, it will look like this, right? This is what our plot of the velocity, the x direction, versus time looks like. But now we have to look at b. We now have a velocity that is in fact moving to the left, and we have an acceleration to the right. And in fact, this right point is our initial time, the left point is our final time, and we see that our velocity vector is getting smaller and smaller. This is the harder situation to think about. Initially, our velocity is large and to the left, which means it's negative, and it's getting smaller and smaller. Now, one hint here is that these acceleration vectors are identical. So what that means is the slope of these two plots must be the same. This plot actually looks like that. We start with an initial velocity that is negative, right? This middle line here should be v equals 0, but it's getting less and less negative. So this is one of the trickiest things to keep track of. The slope here and here are the same. That's corresponding to the acceleration in these two situations being equal, but here we're starting negative, and here we're starting at 0. So please be careful about this. And what would happen if we continued this motion on with the same acceleration? It would actually stop as it reached v equals 0, and it would turn around. So if we started here, it slowed down, slowed down, slowed down, slowed down, and eventually stopped momentarily, but was still subjected to the same acceleration, it would now turn around, head back to the right, which would be plot this part A. So please be careful about this. I find that this is something that trips up students all the time, how you would either think about this motion diagram or think about this plot, but again, this corresponds to a negative velocity and a positive acceleration. So to summarize what was covered in this video, one of the important things to do is to take a motion situation and identify whether it can be simplified to the models that we're going to be working with, specifically uniform motion, which is constant velocity, or constant acceleration. And you might need to break it up into pieces to have each piece correspond to one of these. When you're looking at plots, there's very specific shapes that are going to correspond to uniform motion or constant acceleration. So you should be able to recognize that with the plots and be able to use some simplifying assumptions. Likewise, if you're making plots and you think that you have either uniform motion or constant acceleration, please check whether the shapes of your plots actually make sense. And finally, please be careful about the direction or the sign of your acceleration in terms of your velocity. And remember that it's always the change in velocity, not just the velocity itself.